Hi, this is homework 1, part C, and here I will be deriving the set of differential equations that will be describing the time varying concentration for any number of CSTRs in series. So to begin, I can go ahead and number our tanks, and I'm going to do that such that it follows the indexing of Python. So I'm going to go 0, 1, 2, 3, 4. All right. So for our first tank here, the change in concentration of tank 0 with respect to time is equal to the flow rate going through the tanks divided by the volume, and then that is multiplied by the concentration that is going into the tank minus the concentration leaving the tank. So this will be C in minus C0. And we're able to group these as such due to the flow rate throughout the system being constant. So are able to pull in and group our flow rate times the concentration. So that is for our first tank. So for the second tank, the change in concentration with respect to time is going to be, again, the flow rate over the volume. And this time it'll be the concentration going in is C0. It's what is leaving the first tank. And then you will subtract the concentration that is leaving. So it'll be C1. All right. And then I can keep going. The change in concentration of 2 dt is equal to Q over V times C1 minus C2, and so forth. For any number of tanks, you can do this for number n tanks. Now we will be going into Google Colaboratory and expanding on this problem. Hello. Here we will be working on part C2. We had just derived the system of differential equations that describe the time-varying concentration of number n stirred tanks in series. So now we want to distribute this over 20 CSTRs that are in series, and then we want to model the boundaries of a rectangular pulse of concentration, and then we want to plot two different charts. You want to plot the time varying concentration of the 20 tanks and then plot the concentration profiles. All right, so to begin, we're going to import our libraries. Import numpy as np from scipy integrate. Import solve IVP, and then from plotly dot subplots import make subplots. And we are also going to have to import our sigmoid function, and that is in scipy dot special import expand. We have all of our libraries imported into our code. We can now go ahead and start listing some of our variables and parameters for the problem. All right, so from here we have our total volume is equal to 1 liter. So we can go total volume is equal to 1 liter distributed over 20 tanks in series. So our number of tanks is equal to 20. Now our total volume is 1 liter. However, the volume per tank is going to be the total volume divided by N. And that is the volume per tank. Next, we have our flow rate. It is 0.1 liters per second at steady state with a concentration of 0.1. So we can say Ca is equal to 0.1, and that was molar. And then we need to create a list, or not a list, we need to create an array of values um, of concentrations for each individual tank. So we can do that by saying C for concentration in the tanks is equal to NP dot full, and this will create an array of N tanks, and the value will be Ca. Shift enter, and let's go ahead and check our concentration. Yep, so we have 20 values of 0.1. All right, get rid of that. So now we need to define our function of our concentration in. So define Cn, and that is with respect to T. And for this function, we're going to want the right-hand side to return a sigmoid function with width scaling of 50. Concentration is initially at 0.1, and then with the rectangular pulse, the concentration jumps up to 0.5 molar. So here we'll need to add 0.4, and then we will be multiplying that by our sigmoid function, xpit. And our width scaling here is 50, and we need to shift this to the right once, so we will subtract 1 from T, and that is due to entering the first tank at 1 second. And then once we reach 2 seconds, we will return back down to the 0.1 molar. So we can subtract 0.4, and this will be multiplied by our sigmoid function again, xpit times xpit, with a width scale of 50, and then it is returning back to 0.1 molar at time equals 2 seconds. So here we will take T minus 2. All right. So that is our scaled time shifted sigmoid function of our concentration of our inlet. Enter. Signs between there. Shift enter. All right, nice. So now let's take a look at what our function of our concentration in looks like. So to do so, we will need to create some x and y values to plot. So for our x, we can say t plot is equal to np dot linspace starting at 0, stopping at 10, support 500. Oops. we're going to say fig is equal to make subplots. And then fig dot add scatter x is equal to t plot, y is equal to our concentration in as a function of our x values of t plot. And then lastly, for this figure, we want the mode to equal lines. Enter. Put in an extra number, 0.4, not 48. All right, so there is our rectangular pulse of concentration. You can see we're at 0.1, and then at time equals 1 second, it shoots up to 0.5, and then back down to 0.1 at 2 seconds. We have visually represented the concentration profile. Now we want to define another function, and this will be the, we can just call this the right-hand side. And our dependent variable is time, and our independent variable is concentration. Here we are going to list the expressions that we had previously derived on the whiteboard. So the change in concentration of our first tank, which we denoted 0 for Python indexing, was equal to the flow rate over the volume multiplied by the concentration in minus the concentration out of the first tank. And then change in concentration, the change in concentration of the first tank, or it'd be the second tank, all the way to end tanks is going to be equal to Q over V times C, whatever is coming into the tank minus what is leaving the tank. And here we will need to incorporate uh, some new syntax in order to pull the correct numbers according to each tank. So doing so, I can start with making sure that this is a function of t as it is coming into the tank, and then this is our first tank, so what is leaving our first tank we can call C0. So that is just giving the first, pulling the first concentration from the array. And then changing concentration from the first tank to end tanks. We want to ensure that this concentration value is pulling every single number from the array except for the very first tank. So you can say that it is colon -1. And then we are subtracting the concentration that is leaving the tank. So here we're going to say that this will be our index 1 all the way to the very end. So again, skipping the first tank. And then here we will want to return the right-hand sides of our above expressions. So we can just go ahead and list DC naught, and then the change in our concentration of tank 1 through n. However, we cannot do it just like this. Um, Based off of how we are using it with this syntax, we are going to need to use np dot r underscore, and that is our class. So it's a slice notation. It enables us to basically run through the array and not have to type in these equations over and over again, especially when you have 20 tanks that can get very strenuous. So shift enter. So I'm going to go ahead and drag this over here and just make this full screen. So now we have defined our two functions for the changing the concentration of our first tank and then all the way to end tanks. We now want to solve this initial value problem. So we're going to store the result as result and then solve IVP. And our function here is the right hand side. Time span can go from 0 to t end. We'll need to define that. Our initial guess, just C naught, CA naught. All right, and then our method here is again redow, and then lastly our dense output is equal to true. Close that bracket. Let's check that. Oh crap. I even said I needed to define that still. Okay. 10 is equal to 10. Great. And I just had that defined. C naught, not CA naught. Shift enter. Uh, Shift enter. All right. We have the result for our function here. We now want to plot the time varying concentrations of these 20 tanks. So to do so, we are again going to need to create an array of x values, and we do so by tplot is equal to np dot linspace 0 t end, and then 300 for y values for the y values that will represent the concentrations of the number n tanks. We can call that um, CS for concentrations, and that is going to be equal to our result of our initial value problem above, and then evaluated at the solution, and then of time plot. All right, enter. We can go ahead and define our second figure. So we can go fig2 is equal to make subplots. And then we are going to need to create a for loop, and we are going to need to do this so that when we finally plot our concentration of all the tanks, we can have labels for each individual tank. So we can say for I, we want our concentrations in this will be our y value for our CS. So that'll make sure that we have the correct labeling on our plot, colon. So in this for loop, we will actually add scatter plot. So fig2 dot add underscore scatter. Our x is equal to the t plot, y is equal to c. We again want our mode to be equal to lines. Oops. And then lastly, we want to name our data points. So we will use a f string here, and this will be tank, and then we can go close this. There we go. See what that looks like. Shift enter. Big 2. So here you can see our 20 tanks. I'm gonna update that here. So fig2 update layout width is equal to 800, height equal to 600. I can go ahead and delete that. All right, so this is our first plot, and this is the concentrations of the tanks. Let's extend it a little bit longer. Let's go to 20. So you can see as it initially goes in, the block goes into the first tank, it shoots all the way up, and then you can see that it goes back out around 2 seconds, and then after a short period of time, the concentration starts gradiently moving further and further down the system, eventually dying out after leaving the last tank. The concentration of the different tanks, we are now going to plot the concentration profiles across the 20 tanks at varying times. All right, so fig3 is equal to make subplots. Whoa. It gives us a time scale in this one. For our x, it is from 0 to 1. So our x plot is equal to np dot linspace from 0 to 1 all the way to, there's our x values. So we will again need to use a for loop for this plot. So we can say for I range from 0 to 200 and steps of 10. We can add our third plot, so we can go fig3 dot add scatter. Here our x is equal to x plot, y is equal to our CS, our concentrations of all of our tanks, and then that is going to be with a list of up to I equal to lines. Lastly, here we want to name is equal to our F string, and this will be time times all the way up until 0 to 199. So then we will need to add another line in order to add our 200th point. So we can exit the for loop and then we can copy and paste this. Control V. So fig 3. We need to change our syntax in here to ensure that the 200th point is grabbed from this plot. Lastly, we can get rid of this I in here, and this will be time 200. Control V. Let's change that to fig 3. Shift enter. Full screen. All right. So here is our concentration profiles from 0 to 1 at times all the way from 0 to 200. All right. Thank you guys for watching this part of the homework.